application of momentum integral equation to solve boundary layer problem. And we have overall given the methodology. Last class we saw that we have to वो क्या है ये पूरे बिगड़ गया. Let me start a new note. Now looking at application and we will apply the method for uniform flow past a flat plate. So here capital U is constant, du by dx is 0, and our equation, the momentum integral equation was d by dx of u square theta plus u du by dx times delta star is equal to tau wall by rho. So for flat plate uniform flow, capital U is constant. This implies du by dx is 0. And the equation then becomes u square d theta by dx is equal to tau 1 by rho. So now this is the equation we have to solve. And to do this, that means now theta is not known. We have to solve for theta and we have to solve for delta. We have to solve for tau rho, the tau wall. So all these things we have to solve. And what we said was, we assume f of eta is equal to small u upon capital U, and eta is equal to y by delta. And finding delta is a part of the problem. So we take f of eta is equal to, now this is up to us. And if we take a parabolic profile, let's say, or sorry, a polynomial profile, take it in the form, and I'm taking it fairly general. So I'm taking a fourth order polynomial. And what I want to show here is that this method will, using this method, you will see that we can solve the problem while we are here itself. We don't need to go to any computer, etc. There's some calculations to be done. But now, so what's the first step which we will have to do here? First step is to find A0, A1, एक minute, just wait a minute. So we have to find these constants A0 to A4, and for which we will use the boundary conditions. So the first boundary condition we use is f of 0 is equal to 0. So when we do this, this will imply A0 is 0. Then we use the second boundary condition, which is the essential boundary condition, f of 1 is equal to 1. And this will give us a1 plus a2 plus a3 plus a4 is equal to 1. So these are the two boundary conditions we have used. Now we need three more boundary conditions and we have a choice here. So the first one we use is the one which makes this boundary layer important. That is where we use the information on capital U, and that is f double prime 0 is equal to 0. Because here, this we had discussed in the last class. If du by dx was not 0, then f double prime would not have been 0. And when I do this, I get 2a2 plus 6 eta a3 plus 12 eta square a4 is equal to 0 at eta is equal to 0, and this will imply a2 is 0. So this is, we had four equations. This is one equation comes from a1 plus a2 plus a3 plus a4 is equal to 1. Then we get a2 is equal to 0. Now the fourth boundary condition we will use is, then we go to the top of the boundary layer. We say f prime of 1 is equal to 0. And now you can do this, and what you will get is a1 f prime. So if you have this, f is this. So now what you have here is f of eta is equal to a1 eta plus a3 eta cube plus a4 eta 4. So f prime now will become equal to a1 plus 3a3 eta square plus 4a4 eta cube. And when you put this, f prime of 1 is equal to 0, so we get a1 plus 3a3 plus, this will give us a1 plus 3a3 plus 4a4 is equal to 0. And the fifth boundary condition we use, and now here there's a freedom for us. We can either use the boundary condition at 1 or at 0, and we use it at 1. The, what would be the boundary condition at 0 if we wanted to use? Which is the other boundary condition we could have used here as fifth boundary condition?
Sir, f triple prime 0 equals to 0.
F triple prime 0 is equal to 0. So it's up to us. We use, and I'm just following the method which has been done. So I use this, and this gives me 2a2 plus 6a3 plus 12a4 is equal to 0. So in fact, a2 will has already been shown to be 0. And so this is what this will give you. And this will, when you solve, finally what you get is, when you use all these boundary conditions, you get f of eta is equal to 2 eta minus 2 eta cube plus eta 4, and f prime of 0. This is something which we need because this is related to the shear stress. This turns out to be equal to 2. So these are the two inputs which we get after we put in all the boundary conditions, and these will be put in the momentum integral equation. Now the momentum integral equation is u square d theta by dx is equal to tau all by rho. So first let's work out what is theta. Theta is equal to integral from 0 to delta small u upon capital U and this will become equal to f into 1 minus f dy. So y eta is equal to y by delta. So dy will become equal to d eta, and delta will become like this. And integral from 0 to delta will become integral from 0 to 1. So therefore, once I know f, all I have to do to find theta is basically this thing, if you realize, is just a number. Let's call this as, you can call it n1 or n2, whatever. This is just a number, and let's call this as n1. So now what we get from here is that theta by delta is equal to integral from 0 to 1. Now I put in the value of f is 2 eta minus 2 eta cube plus eta 4, and 1 minus f will be 1 minus 2 eta plus 2 eta cube minus eta 4 d eta. So this is something which you can do it by hand, just numbers, and when you work this out, this turns out to be equal to 37 upon 315, and we, this is what I'm calling as n1. So theta is equal to, now for different profiles, all what will change will be this value of n1. And the, so now you have u square d theta by dx. This will become u square n1 d delta by dx, and is equal to 1 over rho times tau wall. Tau wall is mu du by dy at y is equal to 0. So this becomes mu over rho, I will write it as nu, and du by dy time at y is equal to 0 will become, uh, so this will become multiplied by capital U, so then it becomes f prime, and then I will get a 0, f prime of 0 by delta. So this du by dy, this can be written as d of small u upon capital U multiplied by d by dy. This will be y by delta multiplied by delta. So you get a capital U, and this becomes equal to f prime. This is f, this is eta. So this is equal to, so what we have is capital U square n1 d delta by dx is equal to nu u upon delta times f prime 0. Now this will be the general form for any boundary layer on a flat plate if we are to use this equation. Now we feed n1 is equal to 37 upon 3 pi, and f prime 0 is equal to 2. So we get 37 upon 315 u square d delta by dx is equal to nu u upon delta times 2. And then we can take the variables. Integral delta d delta will be equal to nu upon u times 2 into 315 upon 37 integral 0 to x. I've done the separation of variables and integrated, and this, when you do, this will become equal to delta square upon, now delta, the limit is at x is equal to 0, we assume x is equal to, the boundary layer thickness is 0, and x is equal to delta, this is delta, so we get delta square upon 2 is equal to 630 upon 37 uh, nu x upon u. And from here one can work out delta is equal to square root, is equal to, when I work out, I do all the calculations, do the square root 5.836 mu x upon u. I take a square root, and this one can write delta upon x is equal to 5.83x upon square root of re sub x, where re sub x is equal to u times x upon u. And from here, when we calculate the shear stress will become 0.343 mu u upon square root of u upon mu x. This is what it will come out if you do it calculately and if you do these calculations. And what we find is that this coefficient which we get by just this exercise which we have done in the class is 0.343. And if I just look at what Blasier's solution gave me was, which was Blasier's solution said that this was equal to 0.33. This constant was 0.33 in Blasier's solution. So what we have shown is that by assuming a reasonable profile, you can get a good distribution, you can get all these quantities. And what you realize here is that basically it is this tau wall which is the quantity of engineering interest. How much is the shear stress on the plate as the fluid goes past? And this is what we try to achieve by this momentum integral method. Now we have illustrated it in a very simple case. For this case, even the this thing exact solution or the Blasius solution was available. But momentum integral method is a general method and can be used even if capital U is not constant. Of course, there you'll have to solve an equation which will, another term will come in the momentum integral equation which contains du by dx, which happen to be 0 here. But you can use the momentum integral method and you can solve these problems. So that is what I was trying to. So, and sometimes if you can approximate, so this is 1, 2, the profile in the boundary layer, the velocity profile. And this could be by experiments or it could be by that, then use this for f of eta. And such a solution is used to find shear stress for uniform flow past a flat plate for turbulent flow. See, this velocity profile which we have assumed a polynomial profile, this works when the flow is laminar. In turbulent flow, we have some sort of a power law profile. That is, we will have f of eta will be something like eta to the power of some alpha, where alpha is some fraction, is a fraction, something like 1 over 7, 1/5, and things like this. And there also we can then use these methods to find uh, to solve the boundary layer equations. But the major use of this method came, at least when these theories were being developed, was in case 1, where for any general boundary layer you can work out. Now, With this, we are sort of almost come to the end of boundary layer. But what we realize is in boundary layer theory, if we look at it, what we have seen is, if we look general, that there is some wall, and this could be straight, curved, anything. There is potential flow distribution which is known, and then what we are saying is near the wall there is a thin region which is the boundary layer. Now, one thing is that since we are talking of Re sub x in all these, and which is ux upon nu, and boundary layer works when Reynolds number is much bigger than 1 for large Reynolds number. So the boundary layer equations may not be applicable in a small region near x is equal to 0. That means at the start of the wall. Okay, that is one thing. Secondly, in a general flow, not a flat plate, flow may encounter what is called separation. Have you seen this term before? Flow separation.
Yes, sir.
Any idea what it is?
So
Pipe.
when the cross section of pipe increase with length, then it may occur that water will separate from the boundary of the.
Yeah. But then see, one of the things for flow separation, if this is the direction x, then for separation to occur, a necessary condition is that the pressure distribution in the x direction should be should increase as we go along the flow. This is what we call as adverse pressure gradient. And one of the reasons why this flow separation occurs is, let's think of a flow particle here. Flow, the flow is trying to take the particle in the x direction, but then it encounters a higher pressure as it moves downstream. And it may not be able to overcome. And so as the particle moves, so this is, if the flow is moving, velocity is 0 here, particle near the wall. As it tries to move, if the pressure gradient is large, if there is higher pressure, higher P, lower P, only then you will have separation, because then what will happen is eventually a point will come where the particle will have zero velocity. So the particle slows down, it retards because of this higher pressure. And at some point near the wall, it will have zero velocity. And you may also have flow reversal. So beyond this, you may have the flow may start actually going in the backward direction. And that is what you see when you see sometimes in the flow. You have streamlines like this, but then what you find is there are these regions where the flow starts to take a reversal. And this region where the flow is reversing, this is the separated region. And Clearly, in flow if flow separation takes place, boundary layer equations are not valid, because then this fact that this region, a thin region occurs, thin layer will no longer be there. You have, and the condition at the wall to find separation will be du by dy at the wall is 0, because in the unseparated region the particle moves ahead, so du by dy will be positive. But just at the point of separation, du by dy at the wall becomes 0, and then it becomes negative when the flow reversal takes place in the region very close to the wall. Is this sort of a qualitative picture clear? Can everyone see
So
this
why,
point?
so
Huh?
why do pressure increase if, I mean, flow is occurring?
Well, because that depends on the way the potential flow has been set up. For example, let us say you're asking why the flow increase. If we have a diverging section,
Yes,
what
sir.
happens to the pressure as we move downstream? We are talking of incompressible flow in a diverging section.
So velocity is decreasing, so pressure will
Pressure.
increase. Oh, okay.
So in the potential flow, see, and again, we are talking of potential flows, and that is being imposed on the flow near the wall to get the boundary layer equations. Okay. See,
Yes.
because there is a combination, there is an inertia term, there is a pressure term, there is a viscous term. So it's the inertia term which is carrying the flow on. In this, the flow acceleration is not zero.
Yes, sir.
Okay.
So one more thing.
Uh,
So in
sure.
the, yes, sir.
हाँ पूछिए.
So in the first point, we said that in some region, this boundary layer may not be valid.
हाँ.
Boundary layer equation.
हाँ. Very close to x is equal to 0.
Sir, but in the starting of the boundary layer, we said that I mean, the Reynolds number near x equals to 0 is very high. Then we apply boundary layer equation.
नहीं नहीं. हाँ, see, there the Reynolds number we talked of was the general flow Reynolds number. UL upon nu.
Oh, yes, sir.
Okay. So here what we're saying is, as we do the analysis, we realize in this region, let's say here we are starting maybe in a very small region near x. If this is where the wall starts, so this is the coordinate axis. So here the boundary layer may not be valid.
Oh, okay, sir.
Okay. But then when you do an overall, suppose you're finding the drag force on the plate, then this region becomes insignificant compared to the total flow.
Yes, sir.
Okay. Of course, if you look at books, in fact, there's a full book called Boundary Layer Theory by Schlichting, which discusses boundary layers and other flows. But we have not sort of gone in the details of too much of more of boundary layers. We have just, I've given you, I've tried to, uh, I've, we have seen some of the methods of solving. I've not gone in details because these just become trivial. You can always take a textbook and pick them up. But some of the things which we have seen in the boundary layer, what I wanted you to realize was that basically there's a region of vorticity, region of viscosity close to the wall where you cannot neglect this thing, where you cannot neglect viscosity. Inviscid flow will not be valid, and that is what we call as the boundary layer.
Yes, sir.
Another thing, of course, as many of you realized, the edge of the boundary layer, there is nothing like edge of a boundary layer in a flow. Like if you put if you put colored particles, none of the particles which is flowing will give you the boundary layer. that path, because anyway boundary layer is not a streamline. The edge of the boundary layer is not a streamline. There is flow going past that. So boundary layer is a notional concept if you try to think about it. It is not that there is a particular line, well marketed line in the flow, which you will be able to visualize or see in the experiments if you do, that this will be the edge of the boundary layer. But of course, qualitatively, you can figure out once the velocity gradients become low, then you can say this is where the boundary layer ends, or that's the limit of the boundary layer.
Yes, sir.
Okay. So you should be able to do the order of magnitude analysis for the boundary layer, what we have seen, and things like this. Okay. So, so this sort of brings us to the this thing end of the boundary layer. This thing next, what we will do is we will move to the topic of hydrodynamic stability. But before that, and that's what I'm going to do in the remaining part, a simple thing. I'll talk a bit more of maths. I will talk a bit about eigenvalue problems with eigenfunctions, and we will look at them in the context of solution for ODEs. Because somehow when we talk of ODEs, when you think about it, you'll say, yeah, eigenvalue yahan pe kahan se aa gayi? Let's look at what is eigenvalue. If we look at linear algebra, the concept of eigenvalue is if you have a matrix A, if AX is equal to lambda x, that means we have a matrix A and you find a vector x corresponding to A. That means this vector x will be unique to A such that A times x is now a column vector, is equal to lambda times x is satisfied. Now, when you look at A times x, what are you doing? You are taking a dot product of you are projecting the matrix A on the vector x. And what you are saying is that this projection, when you project it, this is parallel to vector x. And if this happens, then this vector x is what we call as the eigenvector. And the scaling which we get, this lambda, which scales the vector x. So lambda is the scaling or magnification of x. This is called the eigenvalue. So basically the eigenvector is such a vector that if you take a dot product of this vector, if you project the matrix on this vector, the eventual vector which you will get will be parallel to this vector itself, but it may be scaled more or less than 1, and that scaling value is given by eigenvalue. So this is now mathematically, at least when we start doing eigenvectors, you are given a matrix, say you're asked to find eigenvalues and eigenvectors. What do? You take the matrix, you write minus lambda in each of the diagonal terms, take the determinant is equal to 0, solve that equation, that will give you the equation for lambda, and for each lambda you find a vector x. So that is how you practically solve this problem. Now, when you look at this, so solution of eigenvalues, you have matrix A to, so what you do is, if it is A11, A22, A33, A12, A13, etc., You write minus lambda, minus lambda, minus lambda in the diagonal terms, and you put this determinant of this is equal to 0. And then the solution gives you lambda. If this is a 3 by 3, you will get 3 solutions. It's a cubic equation in lambda. You will get 3 lambdas. They may be same or they may be different. So this solution is what will give you the eigenvalues, and x you find by substituting each lambda I in ax is equal to lambda x. So x will not be known. So you put them, and normally when you, if you recall, if you have done these problems, if this vector x has 3 components, you arbitrarily choose one of them as 1 and solve the other components. Of course, when you get the vector, you can make it unit vector by dividing it by its magnitude. You can do all of that. So this is what the eigenvector and eigenvalues are. Now, what does this have to do with differential equations? At least this was it was perplexing to me also. But this is what happens, and we will use this when we do hydrodynamic stability theory. So now let us look at a simple ODE, and I'm sure you know the solution of this. Y double prime plus lambda y is equal to 0, and this equation is a homogeneous equation. What do we mean by a homogeneous equation? What is a homogeneous equation? The right hand side is 0. That means you only have the dependent variable and its derivatives. You don't, in a non-homogeneous equation, you will have f of x on the right hand side. And an example is Laplace's equation is homogeneous and Poisson equation is non-homogeneous. So now to solve this equation, if you recall, we assume this is all in Kreyszig, y is equal to e to the power of rx. So now y double prime will become equal to r square e to the power of rx, and when you feed them in, what you will get is r square e to the power of rx plus lambda times e to the power of rx is equal to 0. This will give you r square plus lambda times e to the power of rx is equal to 0. And so, and the solution for this becomes r square plus lambda is equal to 0. So r square is equal to minus lambda. And now let us say the boundary conditions of this equation. I'll take this y of 0 is equal to c1, y of 1 is equal to c2. These are the general boundary conditions which you have. But suppose if c1 is equal to c2 and both of them are 0, then the boundary conditions are called, what do you think they would be called? What will the boundary conditions be called? They are called, once again, homogeneous boundary conditions. Because now what happens is, and this is where the, so of course in many of these cases, if both the equation is homogeneous and the boundary conditions are homogeneous, you will say the solution is 0. Now, and this is now where the eigenvalue come in, that if the equation is homogeneous and the boundary conditions are also homogeneous, Then a non-trivial solution. What is a trivial solution? Y is equal to 0. A non-trivial solution means y is equal to not 0. Then a non-trivial solution is an eigenfunction, and the corresponding value of lambda for which this solution exists, this is the eigenvalue. And as an example, let us look at the same equation, y double prime plus lambda y is equal to 0. And the boundary conditions we take are y of 0 is equal to 0 and y of 2 pi is equal to. So let us try to solve this equation and let us try to see what I'm trying to say are the homogeneous equations and homogeneous boundary conditions. So now here for this we can have three cases. We have seen the solution r square plus lambda is equal to 0. So we could have three cases. We could have case one where lambda is positive. That means r square is equal to minus lambda, and r, there will be two roots. They will be equal to plus minus square root of minus lambda, and they can be written as plus minus I times square root of lambda times I. Okay, where I of course is equal to square root of pi. Now, if we write the solution for this, so we have y of x is equal to, if you recall what was the solution, e to the power y of x is equal to, we get e to the power of rx. And this, once we have this square root of minus 1, we can put this in the form c1 times cosine of square root of lambda x plus c2 times sine of the plus minus I, which we will have because r e to the power of rx will become e to the power of plus I square root of lambda x and e to the power of minus I square root of lambda x. And this we can write in the form of cosine and sine. The square root of the I, because e to the power of ix is equal to cos x plus I sine x. So this is, we can write it in this form. Now we put y of 0 is equal to 0. This will give us c1 plus 0 is equal to 0. And this gives us c1 is equal to 0. We put the second boundary condition, y of 2 pi is equal to 0. So now this will give us c2 times sine of square root of lambda times 2 pi is equal to 0. Okay. So now there are two possibilities. Either c2 is equal to 0 or sine of square root of lambda times 2 pi is equal to 0. Now this c2 is equal to 0 will give us the trivial solution because both c1 and c2 are 0. So y will be 0. But the second one will give us sine of square root of lambda times 2 pi is equal to 0. This is the non-trivial solution. And what this tells us is square root of lambda times 2 pi. This must be equal to n pi, with n going from 1 to, it could go to any integer. And from here what we get is lambda sub n is equal to n square upon 4. That means lambda 1 is equal to 1 by 4, lambda 2 is equal to 1, and lambda 3 is n by 4, and so on. So we have these values. And what we can do is, so therefore, y sub n of x will be equal to sine of nx by 2. Because our solution was C2 sine root lambda x. We put lambda is equal to root lambda is n by 2. So we get y is equal to this thing. And lambda n, this is the eigenvalue, and sine of nx by 2, these are the eigenfunctions. So for each n, there is a separate eigenvalue and there is a separate eigenfunction. Okay, if we look at the other two cases, we look at lambda is equal to 0. This will give us y double prime is equal to 0. And then we put y0 is equal to 0. Y of 2 pi is equal to 0. And here we will get y of x is equal to c1 plus c2x. And first boundary condition will give us c1 is equal to 0. Second boundary condition will give us c2 times 2 pi is equal to 0. This will imply c2 is equal to 0. So if lambda is equal to 0, we can only have a trivial solution y is equal to 0. We cannot have a non-trivial solution. And similarly, if lambda is less than 0, then the two roots are plus minus square root of minus lambda. Now minus lambda is real. Since lambda is less than 0, square root of minus lambda is real. And here what happens is you can express this as y of x is equal to c1 times cos hyperbolic square root of minus lambda x plus c2 times sine hyperbolic square root of minus lambda times x, where I don't know if you have seen this, cos hyperbolic x is equal to e to the power of x plus e to the power of minus x by 2, sine hyperbolic x is equal to e to the power of x, minus e to the power of minus x by 2. And if we plot this, cos hyperbolic x looks like this. This is 1 cos hyperbolic x, and sine hyperbolic, this is sine hyperbolic x. So now when we apply the boundary condition y of 0 is equal to 0, what we will get is c1 times 1 plus 0 is equal to 0. This will give us c1 is equal to 0. And when I apply y of 2 pi is equal to 0, this will imply c2 times sine hyperbolic 2 pi times minus square root of minus lambda is equal to 0. Now this square root of minus lambda is a positive number. Multiply by 2 pi, taking sign in general will not be 0. So this will imply that once again C2 has to be 0. And so lambda is less than 0 is also a trivial solution. Both C1 and C2 has to be 0. So the solution for y double prime plus lambda y is equal to 0 with the boundary conditions y0 is 0, y of 2 pi is 0. The solution is lambda sub n is equal to n square by 4, and y sub n of x is equal to sine of nx by 2, n going from 1 to up to anywhere. And this basically is valid if lambda is greater than 0. So this is what we get, and these are what we call as the eigenvalues and eigenfunctions. I think I'm going to stop here. In the next class, I will talk a bit more about this, and then we will move on to the theory of hydrodynamic stability. This part, if you can check, it's given in any maths book like Krasik or something. You can have a look at it there. Okay. Are there any questions?
In the second part where we have written that sine of 2 pi root of minus
Yeah.
lambda equals to 0, why we have
So,
not
no,
written?
it should be sin hyperbolic.
Oh, yes, sir.
मेरी गलती हो गई, मैंने एच लिखा नहीं था, अभी किया है मैंने एच. ठीक है, थैंक यू. It should
Yes,
be sin hyperbolic.
yes, yes, yes. Now it's
एंड
okay.
साइन हाइपरबोलिक का ग्राफ मैंने इसीलिए बनाया है, ये दिखाने के लिए कि अगर कोई जनरल वैल्यू होगी तो जीरो नहीं होगी साइन हाइपरबोलिक.
Yes,
ओनली एट जीरो इट इज जीरो. ओके.
yes,
तो
yes.
ठीक है, अभी we'll move on. We'll talk about hydrodynamic stability probably starting Tuesday. थोड़ी सी मैथ्स ही और बढ़ाऊंगा, but again one of the reasons for teaching this is I want to give you a general perspective so that बाद में you people can do what you want. Okay. चलिए ठीक है. Okay, bye. I also have to go somewhere, so I'm not going to wait